For more videos like this for Compact 211, you can check out Sarai Studies. Link is in the description box below. We're told to convert the number 26, that is in base 10, which is another way of saying the decimal number system, the number system we've been dealing with since kindergarten, to binary, and there's two ways to do so, and then to octal, hexadecimal, and BCD. And to do this, we're going to need what I like to call my little conversion table, which looks like this. I do have a video where I show you how to set up this table. There is no need for memorization at all. I'll link it in the description box below and also here at the top right corner. So this table is all you need for dealing with these three number systems. Remember, just like we have different languages like English, Spanish, French to represent the same word, we can have different number systems like binary, octal, hexadecimal, BCD to represent the same number. So for the first method, when going from decimal to binary, look at the word binary. It has bi in it. Bi means 2. That should remind you, oh, I'm just going to divide by 2. What are you going to divide by 2? The only number that they give you. That's 26. So you're going to take 26 divided by 2. That's 13 with a remainder of 0. So not only do we want the answer, but we want the remainder. Remainder of 0 because it divides evenly. Then we just keep dividing by 2 until we get to 0. So what are we dividing by 2? Well, are we going to keep dividing 26 by 2? No, we're going to get the same answer. We divide the answer that we got by 2. So 13 divided by 2, that's 2 times 6, that's 12, 1. So the answer is 6 with a remainder of 1. Then we take 6 and we divide it by 2, that's 3 with a remainder of 0 because it divides evenly. Then we take 3 and we divide it by 2. That's 2 times 1, that's 2, that's 1, so the answer is 1 with a remainder of 1. And finally, we take 1 and divide it by 2. Here's the rule. Once the numerator is smaller than the denominator, then you can't divide something that's smaller by something that's bigger. So the answer is 0, and the remainder will remain stays what you wanted to divide, but you couldn't, so it just stays the numerator. Now, why do we care about the remainders? Because this is our answer. So just count how many you have. 1, 2, 3, 4, 5. That means I'm going to have 5 bits. Now, this is the first number that I see. But you have to remember that the right side is the right side to start from. So we're starting here. So if this is the first number I see, I'm going to start here, and I'm just going to keep going this way. Then I have 1, then I have 0, then I have 1, then I have 1. And this is 26 in binary, in base 2. Now the second method requires us to know how many bits we're going to need before even starting anything. So how do we figure that out? Well, all you have to do is say 2 to the what is going to give us the number we want to convert from, 26. And we're not looking for exactly x, we're just looking for the first x that's going to give us a number bigger than 26. So as a programmer, you start counting from 0. So you start with 0. 2 to the 0 is 1. That's not greater than 26. You could try 2 to the first power. That's going to be 2. That's not greater than 26. Maybe let me skip some numbers. Let's try 4. 2 to the 4th is 16. Still not greater. Let's try 5. 2 to the 5th is 32, which is greater than 26. So the number of bits we're going to need is 5. So we know we're going to have 5 bits. Now, if you don't want to sit there plugging in 5,000 x's until you find one that's going to give you something greater than what you already have, then another way is to construct this table. You can either have it on your cheat sheet for your exam, and if your professor doesn't allow it, no problem, because it's really easy to construct. Like, you don't have to memorize anything. All you have to remember is, hey, I'm in the binary world. Bi means 2, so it's all based on the powers of 2. So that's what you start off with. You just start with the powers of 2, and remember, we start counting from 0, so 2 to the 0, 2 to the first, 2 to the second. You're just writing 2, 2, 2, 2, and then just increasing the exponent. That's all you're doing. And then you actually find out what those powers are. So 2 to the 0 is 1, 2 to the first is 2, 2 to the second is 4, and so on. And then all you have to do is subtract 1 from all of these numbers. So 1 minus 1 is 0, 2 minus 1 is 1, 4 minus 1 is 3, and so on. Now you don't even need the second row anymore. You just needed it to get to this, and this is our table. So how do we read this table? One perspective is, what if I want to represent the number 15, then I'm going to need 4 bits. If I want to represent the number 7, I'm going to need 3 bits. But what if I want to represent the number 26? Where's 26 here? Well, you just locate it. It's between 15 and 31. So then you're going to either need 4 or 5 bits. So the other perspective is, say, okay, if I have 4 bits, that means that I can represent the numbers up until 15. That doesn't include 26. So then you're just going to move on to the next. If I have 5 bits, that means I can represent all of the numbers up until 31, which includes 26, which is right before 31. So that means I'm going to need 5 bits, which is what we have here. Now, I stepped that 2 to the 8, but you can keep going, especially if you have a number like 1,576. You're going to have to locate it here. It's not here, so you're just going to keep adding more powers and then find where 1,576 is. And the rule is, if it's between two numbers, you just pick the one to the right. The exponent tells you how many bits you're going to need. Now you want to write your place values. You want to do your powers powers of 2. Remember that the right side is the right side to start from. So we're starting here and going this way. So 2, 2, 2, 2, 2. Why 2? Because bi for 2. We're in the binary world. And then we start counting from 0, 0, 1, 2, 3, 4. 2 to 0 is 1. 2 to the first is 2. 2 to the second is 4. 2 to the third is 8. And then we have 16. Those are our powers of 2. Now, how do we fill in the bits? So I know I say that the right side is the right side to start from. And yes, keep that as your default. But the only exception is when you're doing method 2, you want to start from the left side. So the algorithm works like this. You take the only number that they give you, which is 26. That's the number you want to convert from. And then you just go through the powers of 2 starting over here. So 16. You ask yourself, is 16 less than or equal to 26? Yes. So 1 for yes. And then you subtract 16. 6 minus 6 is 0. 2 minus 1 is 1. We have 10 as our new answer, our result. Then you move on. Is 8 less than or equal to 10? Our new answer. Yes. So 1 for yes. And then we subtract 8. We're left with 2. Then you move on. Is 4 less than or equal to our answer 2? No. So 0 for no. And then you move on. So you only subtract when you have a 1. Is 2 less than or equal to this answer 2? Yes. So 1 for yes. And then you subtract 2 and you're left with 0. Once you are at 0, you're done. Everything after that is 0. If you had more bits, they would all just be 0. And notice how it's the exact same thing we had in method 1. So this is 26 in base 2. We got the same answer using 2 methods. Use the one that's easier for you. Moving on, what you should do is train your brain so that anytime you see octal or hexadecimal, you think, I need to convert whatever they want me to convert from to binary. So they want me to convert 26 to octal and hexadecimal. But 26 is a decimal number. It's in base 10. So I need to convert it to binary. Whatever in the world they want me to convert from, it needs to be binary because that's what this is based on here. And luckily for us, we already know what 26 in binary is at 01011. Remember, we read the binary numbers from the right. The right side is the right side to start from. So I'm just going to grab this number, and now it's super easy because all you have to do with octal is make groups of 3 starting from the right, because again, the right side is the right side to start from. So starting from the right, this is one group of 3, then this is another group of 3. But wait, I only see 2 digits here, 2 bits. Well, what's here? Nothing. So what does nothing represent? 0. You can write it, you cannot, doesn't really matter. Now the question is, why did we make groups of 3? Well, the same way that another name for the binary number system is base 2, why 2? Because bi means 2. And the same way that another name for the decimal number system is base 10, why 10? Because deci means 10, is the same way that we can say that another name for the octal number system is base 8, why 8? Because octal means 8. So when you think octal, think 8, and then ask yourself 2 to the what is going to give you 8? Well, we know that's 3. So that is why we make groups of 3. And in hexadecimal, we're going to make groups of 4. Do you know why? Because hexa means 6, deci means 10. 6 plus 10 is 16. So another name for hexadecimal number system is base 16. So our number here is 16, and you ask yourself 2 to the what is going to give you 16? The answer is 4, which is why in hexadecimal we make groups of 4. Now we have these groups of 3, but what do we do with them? Well, use the table. You just search for what 010 is. We're dealing within the blue box in octal. This is all we're ever going to need. Here I have 0. That's not it. Here I have 0, 1, 0. What is it in octal? 2. So this is 2, and then what is 1, 1, 0? Because there's a 0 there, there's nothing there. Well, here I see 1, 1, 0, and what is that in octal? 3. So this becomes 3. So we can say that 26 in decimal is 32 in base 8 in octal. Now for hexadecimal, we already know we're making groups of 4. So starting from the right, because the right side is the right side to start from, this is one group of 4, and then this would be another group of 4. But wait, I only see 1 bit. I don't see 4. Well, what are in these 4 bits? Nothing. How do you represent nothing? With 0. So you just have 0, 0, 0, 1. So then what do these groups mean? Well, you use the table. Remember, we're working with hexadecimal, so we're looking at the red box. We're going from binary, so these numbers, to these hex codes. So we're looking for 0101. 0101 in hex is A. So we're going from binary to hex code, from binary to hex code. And now what is 1000? Well, 1000 in hex is 1. So 26 in decimal is 1A in base 16 in hexadecimal. Now for BCD, BCD stands for binary coded decimal. I believe is the easiest out of them all because you don't need to convert a binary, you don't really need anything. Just take the number that they give you, which is 26, and all you're going to do is look at every single digit individually and find out what the BCD code is for that digit. So what's the BCD code for 6? It's 0110. Now what's the BCD code for 2? You find number 2. What is it? It's 0100. And that's it. This is 26 in BCD. So if we're looking from the perspective of BCD, this box here, these are decimal numbers that each have their own BCD code. So far we have converted integers. In the next video I'll show you how to convert using decimal/floats. So I'll see you in the next.